Okay, good afternoon, everybody. At the very last minute, I've been asked to introduce this lecture, so you'll have to apologize for the ad lib, which I will introduce Alexei Lapkin to give this talk today. So I thought rather than, I can't recite Alexei's CV, so I won't try, but instead, perhaps I will give you a short history of perhaps how we've worked together over the last 8 years and to the extent that we're now here today delivering these series of talks from the iDMT. So back in 2015, Alexei and myself started a sort of an initiative that was aimed at bringing synthesis, chemical engineering, and data science together. It turned out that there was more interest in this field across the university than perhaps we had realized. And what emerged from this was two major outputs. One was the EPSRC Center of Doctoral Training, which is called SynTech, for which many of you are members of that training program. And the second was the Innovation Center of Digital Molecular Technologies, which is the center which is organizing this seminar program. And so, as well as it bringing together a huge amount of research across the university, it also brought industry very much into the realm of this newly advancing field of science, because at the end of the day, data science and making molecules are essentially going to be the fundamental future of most molecule making industries. And so what we've established now is a fantastic framework in Cambridge, and Alexei is essentially solely responsible for the vision of the iDMT Center, and he's brought companies into that and merged that with academic research to the extent that this is going to be a huge platform going forward for Cambridge and really part of an extensive network of research and innovation in this general field of digital molecular technologies. So the talk today, Alexei is going to tell us about exploring reaction data for machine learning. So over to you.
Thanks, Matt. So in this lecture series, we're trying to combine the academic talks as well as the industrial talks. And today I'll have to kind of in the middle stop, change my hat, and then start again. So I'll talk about the academic work being done in the research group on data and preparation of data for machine learning. And then I'll move on to how our company, which we've started as a spin-out from the university, is using those now commercially in different tools. So the work which I'm going to show you covers the preparation of data and developing derived data for machine learning. And then when I move to the company side, we'll talk about sort of deeper exploration of the chemical data which exists in different data sets, specifically is exploration of data which exists within Reaxys, and then how do we use it for synthesis planning. And this has been a work of quite a few researchers, so I've put people here who have directly contributed to various aspects of this lecture, but there are quite a few others. So the primary guilty parties for this talk are Daniel and Alexander. I would have asked them to present the technical side, but they are enjoying themselves in Orlando, and I'm talking with you here. So why do we talk about data, particularly within the context of chemistry? What we are trying to do is to create tools for digitally exploring the data and making the workflows in chemical synthesis, in chemical process development, in chemical product development significantly faster and significantly more, interesting, I would say. So in this respect, what we're trying to do is to create these workflows when we go from experiments to understanding what kind of data we've generated, what are those data points, and then merging it with all sorts of existing other chemical data. Either they come in from databases, your ELNs, quantum chemistry calculations, various other possible computational or empirical facts, which then the facts needs to be then converted into knowledge so that you can generate hypotheses, and then the hypothesis needs to be explored. And so all of the aspects of machine learning and AI which are currently being developed, they all rely on various data sources being available, and then this data being prepared for different machine learning algorithms, which then understand what are the relationships between different elements of the data and how those could be moved into then hypothesis generation. When we go into what exists as the data sources, so in one of the papers we've found recently, there is a long list of all sorts of different data sets which exists in the literature. Some of it is private, some of this is accessible. And when we start looking deeper into this, we really kind of beginning to understand that the chemical data is only becoming accessible if it is machine readable and if it is properly structured. So, of course, I have to pay dues to INCHI. We're in chemistry department in Cambridge. So together with Jonathan, we've looked at how do we extend the INCHI format so it includes the reaction process data, and then the records which exist for reaction include process conditions, kinetic information, so that this structured data does not need to be extracted from free text from the publications. And at the moment, there is a very little amount of this kind of data available in databases like Reaxys. It's all in the free text form in the publications. So in this case, if we're looking at this auxiliary layer for reaction INCHI, we include what are the stoichiometries, we include the temperatures, pressure, and then time conversion yield pairs, so that we have the kinetic information accessible through from the records. But it's only one way of doing this. Of course, you can do other types of data structures to represent your chemical data. For a while, Elsevier and Pistoia Alliance were developing a universal data model, which is an XML format which includes all of the possible data facts or facts about the reaction records. The idea was that this is the standard which is being used by publishers to represent data at the back end in the database. Reaxys and Elsevier pretty much stopped developing this. They now pushed it more into Pistoia Alliance, which continue developing the standard for UDM. Now, the real aim for this, when we go into machine learning, is of course to move the molecular information into some form of a Latin space, and whichever favorite model you adopt, whether this is large language models or some kind of graph models or other types of neural networks, in order to then do some learning within that Latin space and whatever target you want to use this for, whether you want to predict properties of molecules or whether you want to predict the reactions or whether you want to predict the entire reaction sequences, that's all up to grabs. The main thing is that you do need to have some data and you do need to encode it. So in the group, we work on various aspects of this problem of how to use machine learning for chemistry. And repeatedly, the same problem always arisen is that the data is never prepared for the machine learning workflows. It always sits in different databases. It's all labeled differently. You don't necessarily know what is what. And it is very, very difficult to combine these data sets into something usable for machine learning. So Daniel and the team have decided to try to tackle this. If you look at the sort of landscape where the data comes in, primarily this is either your electronic notebooks, particularly if you're in industry, those are very rich. If you're in academia, we have access to Reaxys, so in principle, we have manual access to Reaxys, but we also have an academic license to mine Reaxys through an API, or at the moment we also have a flat file. So in principle, we have the entire Reaxys as a data set. There is Pistachio, which is not free. It's a data set which is being prepared by a Cambridge company, NextMove Software. And this is sort of a glorified USPTO data set. USPTO is public. Pistachio is not public because they improve it and they kind of clean it every time, and it's updated quite regularly. And then there is now an open reaction database, which is the project based at MIT, which is slowly growing a data set which is open. The starting point for the ORD was actually a version of Pistachio. So they borrowed a Pistachio at some moment in time, loaded into an ORD. An ORD is a particular schema which is also an XML format. There is also a set of projects under the umbrella of a very large German project called NFDI for Chem. NFDI is a funding mechanism, and then there are quite a few for-something projects. One is for Cut, and it's for Chem, and a few others. They are kind of big 10-year programs. So the NFDI for Chem does quite a lot of work on digitalization of chemistry. So they're also creating the data set. So data sources exist, but in order to be able to use them, you need to clean the data and prepare it for machine learning. So Daniel and the guys decided to look at what exists and how to make it better. There are a couple of workflows which are published, which allow data cleaning, but they're very, very specific. They're designed for a particular data sets and not really easily re-implementable for the others. So instead, they've created the tool which is called Orderly, and which is now, it's on GitHub, it's on a ChemArchive, and it's being peer-reviewed at the moment. What it does, it looks at the data sets which are available within the ORD schema, so the Open Reaction Database, which is still not usable for machine learning because it's an XML database. You still need to convert it and do something useful with it. And the main thing is to take those records and label everything to make sure that you can understand what are the species in those data sets, what are the reactants, what are the products, what are the agents, sort of magic dust you add in, what are the solvents. And then once you have that labeled data set, that is the one you can use for training of machine learning models. Before you've done that, you can't really do that. Then, of course, you need to then benchmark it. What they have in the paper, this is the main product. What they've done also, they have created a few networks and tried to see how it works, whether this is better or not compared to the unstructured, sort of uncleaned data. So when labeling, there are several options. One is you have labeling in the database, and you can just trust it and say the labeling is done correctly. And we found that this is quite often a mistake, because a lot of data is mislabeled. Or you can take a reaction string, which contains a lot of information, and you can learn from that and try to identify what is what by using algorithms. And that generates a slightly differently labeled data set. So for the same reaction, you can generate different labeling depending on how you do it. And one not necessarily is better than the other. So you might actually have to do both in order to test which labeling gives you the better results afterwards. So for example, for this reaction, you trust the labeling. This is how your reaction elements are going to be labeled. But if you use the reaction string and use the logic behind that string, then the labeling is slightly different. And so obviously, you start training the machine learning models, they will have different inputs. And so the way how they will behave afterwards is different. When you look then into the data, starting from ORD, which is pretty much Pistachio some time ago, you have a full data set which has about 1.7 million records, reactions. By the time you've cleaned everything, if you trust the labeling and you delete everything you don't believe or you don't trust or it's missing data, you only have 75,000 left. And if you do a reaction string labeling, you have a little bit more left. But still, the size of the data set dramatically reduces. So from what you think is a huge data set, when you end up with a machine learning ready data set, it is significantly smaller. We've been doing something similar for Reaxys, and the Reaxys has 56 or something like this million reactions in it. By the time you prepare a data set which is machine learning ready, it reduces to about 15 million. So it is a significant drop in the size of the data set after you've cleaned it. If you don't clean the data set, most of your models will be pretty much wrong. The model accuracy increases as you clean the data sets. There are quite a few tricks in there, and one of them is, what do you do if there are very, very few records about specific molecules? And this is quite common in chemistry. You could have reaction records, and I'm going to come back to this conversation a bit later in a different context. You sometimes have a unique reaction record, and there is just nothing else around that chemistry. Nobody has followed it, or people have forgotten about it, or people have never used that reagent again. If you have situations like this and you try to use this kind of data in machine learning, your models may become less accurate because those facts are unique and there are no repeated data around this. And so it creates a problem for, it depends which kind of machine learning models you use. So one of the things which Daniel has done is figuring out how frequently certain agents are labeled as having those kind of functions in chemistry. And if they're labeled like this very, very rarely, remove them, because they might be errors. He doesn't know that they are errors, so he might be missing something very useful, but at the same time, it kind of makes it a bit more confident about the larger data set. So he's removing some unique molecules which doesn't pass his filter. So after he's done this, then he's created a few data sets, and he shows that the clean data set progressively perform a little bit better. So the green label, the green percentage figures are how much better the clean data set, the models trained on the clean data set perform compared to the models which are trained on the unclean data set. So there is a clearly benefit from creating the clean data sets for this kind of tasks. So switching gear, let's say we have reasonably good data sets. We now want to put it into practice, and we want to do machine learning tasks. And this is the piece of work which we've done together with Matt, using the high throughput data from his group. And we were interested to understand how do we really move the data into a machine learning model? What sort of molecular representations we need to use? Because molecular information is really molecular structures, information about reaction conditions. These are kind of obvious for us, but it's not very obvious for machine learning models. So we need to have some kind of translation. So if we take this chemistry, there is, of course, quite a lot of knowledge in the literature about what that chemistry is, what is the mechanism, what are the ligands, how they work. This is sort of fundamental knowledge. This is sort of classical knowledge of chemistry, which is represented in scientific papers. This is pre-machine learning, this is pre-AI workflows. In order to convert this knowledge into what machine learning models can use, we need to parameterize this. And there is a very large diversity of methods which allow you to do these parameterizations. So Alexander, who's been doing this work, was looking at different ways of doing it. The first, which is the very simplest, is called one-hot encoding. It basically says, I'm not going to parameterize these molecules, I'm going to just list that they are there. And that's it. I'm just going to say, I have 32 ligands to try, I have 3 catalysts, I have 2 boronases, other components in the reaction mixture. I'm just going to make sure that I have a record which says it's there or it's not there. And that's it. Just presence of a particular type of molecule without actually any chemical knowledge about what that molecule is. And then a variety of methods which are progressively more expensive. There are classes of methods which are called molecular fingerprints. You take your molecule, you look at what is the reaction center, you step out one atom or one bond from there and look at the atoms around and you parameterize. What are those atoms? What are the bonds? What are the angles? So you create a fingerprint. If you want to be a little bit more data rich, then you step out a bit more. So you have a second sphere. And then depending how much or how rich your fingerprint you want, you can step out multiple sort of bonds away from the reaction center. And there are typically, let's say this is Morgue fingerprint with 2 radius or 2 bonds out of the reaction center. You have 3,000 features in the vector which you generate, which is computed by standard chemoinformatics software. And then beyond that, you go into really, really expensive descriptors, which then take into account stereochemistry, the structure of the molecules, and also the electronics. So you do density functional theory, and you extract descriptors from density functional theory calculations. So you're looking at things like percent buried volume. If you're looking at the stereochemistry, you have ligands, and you're looking at some kind of features, how stereochemistry is induced. So you need this information about ligand. The stereomol is another descriptor which allows you to characterize the sterics of the interaction. So ultimately, in this work, we analyzed 14 different ways of parameterizing the data, which you then use in a machine learning model to then try to do a prediction of how this chemistry actually works. Now, the result I'm only going to show you one is actually quite interesting, which shows that actually the simplest way of doing it, just labeling that the molecule is there or not, is the best compared to everything else. This works in this case because we had access to a high throughput data set. We could actually try a lot of options. If you have that luxury and you can try almost everything, you avoid having inaccuracies of the descriptors, because you don't actually know which descriptors are better, how correctly they describe the mechanisms, how correctly they describe the interactions. That is unknown. You need to learn that somehow. If your data doesn't allow you to learn that, you might not have the right combination of the descriptors. So they all the methods eventually learn something, but they learn it with the different rates. And the one-hot encoding is the model which learns the fastest and gives you good predictions in this. So this is sort of I would say, state of the art for us in preparation of data, working with the data sets, and then looking at how do you convert the chemical data into derived data, which then, on top of that, you can start building the machine learning models. And I'm not going to go into what are machine learning models and so on. That's a different topic. We have a couple of people coming to talk about this in this series later on in January. So now I'm going to switch gear and talk a little bit about what we decided to productize. So a few years ago, we formed a company called Chemical Data Intelligence, and I'll show you why we've started this and what gone into developing the company and what the company does now. So we've been working on this kind of questions, which are sort of multi-step synthesis questions. If, for example, I want to do something crazy, like make paracetamol out of limonene, I don't know why would I want to do that, but let's say I want to do that. Then somebody can come up with a route like this, and somebody did come up with a route like that. And then the question is it the best route if I want to start from limonene to make paracetamol, or is it not? This turned out to be quite a big problem to solve. There are 6 steps. Some of them are quite tricky. So we started looking at something a little bit simpler. if you start looking at this smaller question, let's say if you want to go from limonene to benzoic acid, if you just look at reactions and how many records are in reactions which allow you to do that, there are 232 potential routes for 3-step sequence. It's not many reactions, but there are very, very many options. So if you want to find the best, you need to somehow figure out how do you enumerate all 232 options and find the best ones. This is pretty much impossible. It's too much work. So we need to do it automatically. We need to figure out how do we enumerate those options and then create a software around this. We're coming back to the limonene. After trimming, so after taking 232, looking at what's there, removing all the nonsense, going from limonene, which is over there, you don't have to see that, to paracetamol, which is over there, you have a rather complicated reaction network. So every node here is a molecule, and every arrow is a reaction. The thickness of the arrows corresponds to how many times those reactions were actually reported. So those reactions are either popular or not popular. Now, in this work, when we were looking at this, and this was still done academically, we realized that there is one reaction, which is that one here. Doesn't matter what it is. I actually don't want to show you what it is for a reason. It's a reaction which was reported in 1919 and never repeated and never cited. And the product is a byproduct. So I don't want the main reaction, I want a byproduct of the chemistry which is reported. And so it's a reaction which is not obvious how to do it, but it seems like it is chemically feasible because it is a byproduct in the chemistry. So there is a chemical path to that reaction. I just don't know how to do it. But it turned out to be extremely important in the network because it opened a lot of different chemistry. If I could do that, I could do all sorts of different reactions, which I couldn't do before, within the network. So looking at these things, we realized that there is actually quite a lot of interesting stuff we can do by analyzing networks of reactions, looking at all of the possibilities and looking at it as a graph problem. It's a mathematical graph problem. And the mathematics of graphs is actually quite well developed. So, one of the things we've done recently, and this has just been published, so the accepted paper is out, is starting to use this. How do we generate ideas about new chemistries which could be then tested in literature? So we have a collaboration in Singapore with Professor Ning Yan. He is interested in using biofeedstocks to make various kind of molecules, and he identified that this one, which is called pyrrole 2-carboxylic acid, is quite an interesting precursor because it's used in different type of bioactive molecules. But the published chemistry is not very nice. It all uses ammonia. If you use ammonia, that means that you're pretty much going back to petrochemistry because most of ammonia is produced from Haber-Bosch. So it's not particularly green. So let's try not to use ammonia and use something else. So for example, you can start from chitin or some version of this because ammonia is already there. But there was no pathway to this intermediate from any of the renewable sources. So he threw this problem to us, and the problem then is try to assemble all of the data which exists on biofeedstocks which contain nitrogen and oxygen, and then all of the chemistry which can take us from there to the PCA, and then somehow rank those reactions and figure out what looks interesting. So we've done that, so assembled the data, created the network, did the route search, and then do the ranking. I'll explain you, I'll move now into the way how the company does it. And we found that this reaction seems the most interesting. So there was a record of something similar to what we want to do, but it was a 1955 paper with the reaction conditions which actually were given very, very low yields. So then we gave it to the chemists, and then the chemistry magic starts, which is something I cannot do, is how to actually make it work. So the guys made it work. It's not perfect, but at least for a number of this kind of keto acids, number of these keto acids, you can make various derivatives of PCA, and some of them are in relatively decent yields. So because they're quite different from the starting materials, the separation is actually not that difficult. So we're not particularly bothered that the yields are not high. The separation is not very difficult for this. So this is kind of an example of how we could use access to data and access to reaction networks. So when we were doing this, we had quite a few companies who are end users who said, why don't you productize this? So we did that. So we started a company in 2020 with a then PhD student in the group and a postdoc in the group. We had some money available in the university has a Singapore site called CARES, and they had some money. So we asked them, could you kindly give us a grant to start a company? And they gave us a grant. So we had some money from them. And then we had access to a professor in IFM who was also contracted to CARES to do some commercialization work. So we had a commercialization guru for free. So we had quite a few workshops with this guy who basically taught us how to formulate what the value proposition is, who are our clients, and so it was very fun. I knew nothing about this before. So we had quite a lot of help, pretty much for nothing. And then we, I would say, signed up, but it's still not on paper, created an agreement with Elsevier that this is a commercial partnership with Elsevier. We will be using their data in productizing this. And then the interest from us and from Elsevier as well, that we focus on the questions of bioeconomy, circular economy, resilient supply chains, to develop tools which allow to explore questions around this. In sort of preparation of this, one of the last things Jana did in the group was to publish this review on what exists as a state of the art, 2 years ago, around chemical data. So what kind of data sources exist, what kind of metrics exists on analyzing the data, and then the chemistry, how do you do decision making once you've enumerated the metrics, whether you do life cycle assessment or cost estimates or some kind of other ways, and how do you assemble all of it into code. And then we also proposed sort of a time frame. How do we get to the situation when everything is productized? And we're not entirely there yet. So we're kind of 2 years after that paper, we're sort of somewhere there. We're still working on some of the aspects of this entire workflow, how to move all of these aspects from data standards to various kind of informations to metrics into the overall code. So what do we answer? We've done a few of these things with companies. One question we had from a company I can't name, who has a large product. It is produced from petrochemicals, and they asked, is there a viable way of making the same molecule from new feedstocks, whether they are bio or methane or CO2? And then we found all the chemistry which allows them to do that, rank it, and found that there is a route from methane which is potentially even better than the one they use commercially. So the reason for doing this by these companies is pretty much future-proofing, as well as identifying what do they need to work on, as well as IP protection. So if somebody has information about the same, they could develop a new route which is not patented and effectively have access to a very large product for free. So I don't know what this company does with this information, but if I were them, I would patent the alternative route just in case somebody does that. We also looked at potential evolution of the networks to look at sort of future scenarios. What will happen if you develop new chemistry? So where there is potential to use particular molecules if they come from biofeedstocks. And also we could look at what are the most important molecules and what are the most important transformations within the context of particular questions. So you can have a company and they could ask a question, what should be our stock so that we can do most of our chemistry? Or what are the most important reactions we need to focus because we repeatedly doing the same type of products? So these are the kind of questions which we can answer. So what is now productized is pretty much described, we've published it in the paper last year, is what's in our codes, is how do we define the problem. So it's an environment for the chemists to define what do they want to do, how many steps in the synthesis, do they want to do forward synthesis or retrosynthesis, do they want to explore reactions out of one molecule. Then the data mining is done underneath. The data treatment is done with the interaction with the chemist. They could say, okay, I got too much data back. If you just open and say, give me everything, you might get back several million records. You can't deal with that, so you need to trim down the data. We let users to say, well, I don't want any metals in my chemistry, or I don't want any halogens in my chemistry, or I don't want anything which is patented. We have records of what is patented. And then those will be removed, so they see a trimmed data set. Then the pathways are assembled into networks. The number 5 is quite interesting. I think I will show a little bit of that, how we do this, because the data is sometimes augmented with derived data. After that, we go into enumerating various metrics. I think I show you what they are, and then we give the outcome. So all of this is encoded, and effectively we kind of have it as a code which sits on the cloud, which does your root, and we hope people will use it to develop better chemistry starting from renewable feedstocks. But to be honest, until now, most people who are interested are process chemists in pharma companies, rather than anybody else. They really they know what to do with it, or process chemists in specialty chemical companies where product turnover is very fast and they have to develop chemical routes quite a few times per year. So in the product, we start with the data, which in our case is Reaxys. We now augment it with anything else we can find. Then, based on what the features are added, so for example, remove all the halogens or remove all the metals, we change that data set so that it's smaller. So we create a customized reaction data set. Then we create a network. So once we have a network, we then can search different paths within that network. So this is network traversal algorithms, which are quite common. And we do it in 3 different ways. The first one is there is a known molecule, let's say known feedstocks, there is a known product looking at only known chemistry. That's the simplest one. There is another one is you know the product, but you say make it from anything or make it from all the biofeedstocks. So then we do this. And then there is another one where we don't like how much data we have and we effectively create new chemistry which is rather hypothetical. So I'll explain how we do this. So let's say you have a target chemistry. So this is the reaction you want to do this ring closure. There is actually no record of this in the literature as a single step. There is a record of this in the literature as a 2-step chemistry. I want to do it as a single-step chemistry. We map what is the reaction center. We map the functional groups which are around reaction center, and we map what is a scaffold. So we represent the molecules something like this. And then we search in the data set all of the records where this reaction center actually does this kind of transformation. But the functional groups are different and the scaffolds are different. So we're making a huge assumption that the functional groups and the scaffold doesn't matter, which of course is wrong, but I'm not after predicting exactly how to do chemistry. I'm after any ideas from the overall knowledge of chemistry that something might theoretically be possible. And I don't mind if I'm wrong at this point. I just want some ideas out of the sort of literature which exists in reactors, because those records could be in a completely different literature domain. So if you are in medchem, you might need a transformation which somebody in polymers have done ages ago, and you've never seen this. And so you wouldn't go there for that kind of knowledge. And this way kind of decontextualizes this and opens up everything in the data set to be searched. So we search for all of the possible analog reactions which does that, and then present options to the chemist. So we actually found a record which does something similar, a similar transformation, with really not a very good catalyst, but it does exist. That means that I could work on it, I could figure out how to change that catalyst and make it much, much greener and make it much more useful. So this is now encoded, and this could be, we use it for a number of different workflows. The same workflow we use for impurities prediction, throwing molecules into a different environment and seeing what could happen if you have different reagents, what kind of impurities they could make, and so on. So the kind of things, again, similar example from terpenes type chemistry. We worked with BASF, and they asked, find all the different ways how to make L-menthol. The reason is very simple. It's one of the biggest products for BASF. They make hundreds of tons of this per year, and they're building a new plant in India to make even more hundreds of tons of it per year. And they were basically looking at, did they make a right choice that they're going to do exactly the same process as they do in Ludwigshafen in India, or they need to do something different? So we basically screened how you can make it. This is how they do it now from isobutene. You can make it from CO2, you can make it from methane, you can make it from terpenes, and then this goes to process chemists to understand, is it sensible to actually do it? Access to feedstocks, all the costs, all the technologies underneath it, and then they make a judgment whether this is a good way forward or not. So after sort of finishing productizing this, we have a synthesis planner. It's a software. It's not represented here. It's basically, there is a user, they have a user interface, and they can do all sorts of things. Choose feedstocks, choose products, how many routes, different filtering, what do they want to inspect, routes, networks, we have graphics of networks. Do they want to do analog? We also implemented chiral reactions, because that is a particular problem in retrosynthesis. And then they have the output in there. What we did recently is we've compared how this product differs from what's published as retrosynthesis tools and what's particularly, because we're going to be competing with the same Elsevier tools. So there is a retrosynthesis tool in Reaxys. So the published Reaxys data only allow you to extract about 10 records, about 10 steps. It has some resources in the building blocks. The yields are probably most of the time missing. The retrosynthesis prediction tool actually has quite a lot of limitations in terms of what it can deliver as a number of how many routes it can search, how deep is the network it searches, how many branches it will search in order to give you the answer. And those limitations are pretty much removed. So we search a lot of branches. So if you have a retrosynthesis route, you get to the molecule earlier, you explore the branch from there, which is not done in any other retrosynthesis tools. You can specify all sorts of building blocks, and You can also do a lot of analysis on undesirable functional groups, looking at different metrics. There is a metric on similarity, there is a metric on environmental impact. You can look at these analog roots and the chiral reactions, and it also provides you a network, which Reaxys doesn't do. Cynthia does, is another commercial product which exists. They build you a network, and you can see how it looks like. So this is then the product which the company is now in the process of final testing and launching. And that's it. That's all I wanted to talk about today. So I've put on the acknowledgement with all of the people who do fund us for different academic work, and particularly big thanks to Elsevier. They've enabled us to access Reaxys over the last pretty much 10 years, and that gave us a very good kind of basis to do a lot of academic work and think about potential productization or commercialization routes for these technologies. And I think I left enough time for questions.